everybody, I am Zehra and today we are going to talk about chapter 11 of critical thinking, and our topic is inductive reasoning. Let's begin with what's inductive reasoning. An inductive argument is one in which the premises are intended to provide support but not conclusive evidence for the conclusion. And an inductive argument is strong when the premises provide evidence that its conclusion is more likely true than false. And an inductive argument is weak when its premises do not provide evidence that its conclusion more likely true than false. For example, most critical thinking students improve greatly in their ability to analyze arguments, so you will probably improve greatly in your ability to analyze arguments. It's an inductive argument. The reason of it has a single premise dealing with a general group. Most critical thinking students, and a conclusion about a single specific student, you. And is inductive because the premise provides support for the conclusion, but the premise is not intended to guarantee the conclusion. And if the argument's conclusion does not follow with strict logical necessity from its premises, the argument should always be treated as deductive. And if argument's conclusion does not follow with strict logical necessity from its premises, the argument should normally be treated as inductive. And another important aspect is this is an inductive argument because there is a word of probably, as we have seen in chapter 3. We call such words induction as indicator words. Among the indicator words and phrases for inductive arguments are likely, it's possible to suppose that, and it's reasonable to believe that, one would accept that, it's a good bet that, chances are that, and odds are that. Most of these phrases can be and often are used in making prediction. And another way to identify inductive argument is to look for their common patterns. Four of these are inductive generalization, statistical argument, argument from analogy, and causal argument. And we are going to elevate them one by one in this chapter. And let's begin with inductive generalization. A generalization is a statement made about all or most members of a group. And an inductive generalization is an argument that relies on characteristics of a sample population to make a claim about the population as a whole. Here is an example to understand better. All the bass Hank has caught in the Susquehanna River has weighed less than 1 pound, so most of the bass in the Susquehanna River weighed less than 1 pound. When we look at this example, the sample population is the bass Hank has caught in the Susquehanna River. The population as a whole is all the bass in the Susquehanna River. Inductive generalizations such as in this example fit the stereotype of induction. The argument moves from a specific premise to a more general conclusion, but we should remember that the important thing about inductive argument is that the truth of their premises is not intended to guarantee the truth of their conclusion. In that way we say them generalization. And here is inserted other example. Inductive generalization should not overstate their conclusion. No rabbit Alan has come across has tried to attack him, so most rabbits are not included to attack human being. As we have seen, there is not enough evidence to for conclusion, so we say that inductive generalization. And when it comes to evaluating inductive generalization, here are some things that we should pay attention into. Firstly, we should ask ourselves that are the premises true. For example, most CEO of Fortune 500 companies are women, so the CEOs of most big business are probably women. The premise in this argument provides strong support for conclusion. After all, if most of CEOs of most financially successful big business are women, it will seem likely that the CEOs of most big business are women. The premise is false. However, most CEOs are women, so it cannot legitimately be used to support the conclusion. The argument is not cogent. And other thing is none of is the simple large enough. And here's an example. None of the thousands of rabbits Alan has become across and try to attack him, so most rabbits are not included to attack human beings. Thousands of encounters with rabbits seems like a large enough sample size to support the modest conclusion that most rabbits are not included to attack human beings, so no inductive argument can guarantee the truth of its conclusion, but you don't have to be an expert in statistics to see that this one is a pretty good bet. And here is the other thing is the sample representative. We should pay attention to it also. 2 nuclear bombs were dropped on Japan, and today Japan has one of the strongest economies in the world, so all the concern about the nuclear warfare and the end of humankind is a bunch of nonsense. The 2 nuclear bombs dropped on Japan and devastated that country, but the Japanese have recovered well. The use of 2 nuclear bombs, however, is not enough to tell us what would result from the use of nuclear bombs. They are not large enough sample. Beyond that, those nuclear bombs may not be like other nuclear bombs that could be used, which leads us to third question. And now let's move on our other part, opinion polls and inductive generalization. Opinion polls are an excellent source of inductive generalization, and the aim of poll is to determine what a large population thinks or believes about a certain issue. And we can use polls to arrive at a level of 95% certainty that a sample population will mirror and the population as a whole within a small margin of error. And the margin of error is usually indicated by a combination of plus and minus signs, as we seen here. And this means that the results will be within a range of plus or minus the amount indicated. Here is an example. The latest poll shows Sacamano leading Lomez by a margin of 60 and 40 with a margin of error of 3 plus minus. This suggests that there is a 95% chance that if population as a whole voted, the results would be somewhere between 63 and 37% and between 57 and 43% in favor of Sacamano. As we have seen, In first scenario, we add 3 to 60 and we minus from 40 to 3, so our result is 38. Or other scenario is we minus from 60 minus 3, 57, or we 40 plus 3 equal 43, and in the favor of Sakamano, this result can be between them or between them. And now let's turn to our other part, statistical arguments. A statistical argument argues from premises regarding a percentages of population to a conclusion about an individual member of that population or some part of that population. For example, 90% of college students are in favor of not having a cumulative final exam in their critical thinking class. Vera Peterson is a college student, so Vera Peterson is in the favor of not having cumulative final exam in her critical thinking class. Let's eliminate this example. A statistical argument is strong when it provides evidence that its conclusion is more likely true than false. That is, when the chances that the conclusion is true are greater than 50%, and a statistical argument is weak when it provides evidence that its conclusion is more likely than 50%, weak, less than 50%, and more than 50% is strong. And the preceding example is thus a strong argument, providing evidence that there is 90% chance its conclusion is true. And the evidence does not logically guarantee that the conclusion is true, but the evidence in inductive arguments never does. If I give another example, only 3% of Wexford College students are against building the new gymnasium. Johnny Z is a Wexford College student, so Johnny Z is not against building the new gymnasium. This is a strong argument offering evidence there is a 97% chance that the conclusion is true. But we can make stronger this argument by adding probably to the conclusion. For example, so Johnny Z is probably not against building the new gymnasium. If we say, if we add our arguments probably, likely, it would be more stronger. Let's move on. Reference class. It refers to it's the group to which a statistic apply, and the more specific the reference class is, the better the argument is. So we should try to make it more specific. Our reference class should be more specific, because the more specific the reference class, the better the argument is. So we should try to do that. And here's an example about reference class. 89% of Wexford students who took Watkins critical thinking course voted for Walking as teacher of the year. Alan is a Wexford student, so Alan probably voted for Watkins. Let's add more info to arrive at a different argument. The first is the same. The second one is Alan took Watkins' critical thinking course. So Alan probably voted for Watkins Teacher of Year. As we seen, we add Alan took Watkins' critical thinking course. We have changed the reference class, becoming more specific in the second argument. Now we are no longer talking simply about Webster students, but about Webster students who took Watkins' critical thinking course. The change in the reference class in this case changed the arguments, though the conclusion remains the same, from a moderately strong but unreliable one to stronger and more reliable one. And let's move on. How can we argue by analogy? An analogy simply points out a similarity. An argument from analogy claims that certain similarities are evidence that there is another similarity. And A has characteristic X. The post office is a government agency. B has characteristic X. The Department of Motor Vehicles is a government agency. And the post office is closed for the Martin Luther King Day. A has characteristic yeah, and so the Department of Motor Vehicles must be closed for the Martin Luther King. Therefore, B has characteristic Y. Let's have a look evaluating arguments from analogy. When we evaluate arguments from analogy, we should pay close attention to these criteria. The first is the truth of the premises, is our first criteria, and then we should pay attention to the relevance of the similarities and the number of relevant similarities, and the relevance of the dissimilarities and the number of the relevant dissimilarities, and the diversity of the sample, especially with the increased sample size, and the specificity of the conclusion relative to the premises. And let's have a look induction and causal arguments. Inductive arguments that try to identify a cause and effect relationship. And when we search for the cause of a certain effect, we are looking to identify a certain relationship between two things or events that is a relationship. And one piece of supporting evidence for a cause and effect relationship between things or events is that one thing regularly comes before the other. For example, every time you let go of your coffee mug, the coffee mug falls to the floor. In this example, you assume that there's a cause and effect relationship at work between the release of heavy object and its falling to the ground. And not all causal arguments contain the word cause. Other causal terms indicate produces, such as is responsible for the effects, makes, change, contributes to. These are the indicator of causal arguments, cause and effect arguments. And such arguments come in two broad types. The first type is arguments about cause of a single instance and arguments about a general relationship. Let's have a look at them. Argument about the cause of a single instance. Megan's car wouldn't start this morning, and she hasn't replaced the battery since she bought the car 6 years ago, so it's probably a dead battery that caused the car not to start. And in the second example, the Surgeon General has found that there is a strong link between smoking cigarettes and getting lung cancer. So smoking cigarettes cause lung cancer. In each case, it should be clear that the argument is inductive. And the premises provide evidence, strong evidence for the conclusion, and the conclusion does not follow with strict necessity from the premises. It's always at least possible that the premises are true and the conclusion is false. Given what the argument says, it is at least possible that the car's alternator is shot and the battery is fine. Of course, there would be ways to investigate the matter further, but the argument as it stands does not do so. Given only what the second argument says, there is no guarantee that smoking is the cause of lung cancer. Two things can be linked without one causing the other. And let's move on the other feature of a causal argument. Some causal arguments are intended to be deductive. Whenever iron is exposed to oxygen, it rusts. This iron pipe has been exposed to oxygen, therefore it will. The relationship cause and effect have been established well, and not only has iron exposed to oxygen rust repeatedly, but there is also a sound scientific understanding of why this occurs. Aside from his skeptical concern about observing cause and effect, this is very well established causal argument, so it's a deductive argument. So we cannot say that causal arguments are always inductive. They are sometimes can be deductive also. And let's move on correlation and cause. Sometimes two things or events are clearly associated or linked. Where you find X, you will find often that a relationship such as this, in which two things are frequently or even constantly found together, is called a correlation. In a correlation, two things share a mutual relationship where one is found, the other is often or always found. In contrast, in the relationship of causation, one thing produces or brings about the other. Sometimes a correlation is an indicator of a cause and effect relationship. For example, the high rate of lung cancer deaths among smokers led to the investigation and discovery of a causal link between them. We must be careful though. Most correlations do not indicate a causal relationship between two things or events correlated. For example, there is a strong correlation between shoe size and average ability in math among children. The larger the shoe size, the greater the average ability in math. For example, on average, children who wear a size 8 shoe score higher on the same exam than those who wear a size 6 shoe. Does this imply that having the large feet causes an increase in mathematical ability, or does it suggest that mathematical ability causes feet to grow? Of course not. There's an underlying explanation for this phenomenon. A child age is correlated with both shoe size, and mathematical ability. As a child grows older, both shoe size and mathematical ability tend to increase, but neither one causes the other. It's just correlated, but not it causes the other. We should know the differences between correlation and cause. And there are two types of correlation. The correlation of two things or events can be positive or negative. A positive correlation, one that indicates two things are found together more than 50% of the time, may indicate a causal connection between one thing and the other. and a negative correlation, one that indicates two things are found together less than 50% of the time, may indicate that one thing prevents the other. And let's move on. Probability. There's an important connection between probability and induction, so we are going to have a look correlation between them. And all inductive arguments are a matter of probability because they are not certain. So we think this type of argument as inductive because there is not any certainty about them. If we have not sure about anything, we use the word probably, maybe, likely. We use these indicators when we are not sure about anything, as I said before. And here's an example about probability. There is a pretty high probability that I'll go to the beach sometime this summer, and there's a 50% probability that the operation will be successful, and there is a 50% probability of getting tails on a fair coin toss. And the first example, there's a pretty high probability that I'll go to the beach some time this summer, illustrate epistemistic probability. And epistemistic probability is the kind of probability we assign to things we have good reasons to believe, and but to which we cannot assign a probability on any truly mathematical basis. And this is the kind of probability we assign statement we believe, but to which we cannot assign a probability. And knowing that I want to go to the beach sometime this summer, and believing with good reason that I will have time to do so, I can rationally assert that there's a high probability that I will intend to go to the beach. And along the same lines, we can also assign low probabilities to the certain events. For example, considering the way Sid and Nancy were arguing last night, I'd say there's a pretty low probability that they will get married. And the second example, there's a 50% probability that, which takes this example illustrates relative frequency probability, which takes information about a group as a whole and applies it to an individual case. And the application is based on accumulated data derived from what has already been observed in the group. And the third example, there's a 50% probability of getting tails on a fair coin toss, illustrates a prior probability. Statements that have odds that can be calculated prior to and independent of sensory observation. Even if I have never seen a coin before, you can explain the nature of the coin toss, and I'll be able to tell you that the probability of the coin coming up tails is 50%, and the probability of this coming up heads is likewise 50%. The same would be true of a deck of cards. Even if I have never seen one, you can explain to me that there is a total of 52 cards with 13 different values and 4 different suites. I can then tell you that the chance of any particular cards being drawn is 1 in 52 or 1.92%. The chances of an aces being drawn are 4 in 52 or 1 in 13 or 7.7%. And the gambler's fallacy is the mistaken belief that a past event has an impact on the current random event. And according to law of large numbers, the proximity of theoretically predicated and actually percentages tend to be increased as the sample grows. In other words, the bigger the sample, the closer the actual results are likely to be predicated results. And expected value is essentially the payoff or loss you can expect from making a bet. And relative value is the value of bet has in relation to an individual's own needs, preferences, and resources. And diminishing marginal value is the principle that as quantity increases, the relative value tends to decrease. That was all, and thank you for listening.